that we design an algorithm that limits the number of Sybil IDs in an open system such that it provides the following guarantees. The two guarantees that we want are correctness and efficiency. What we mean by correctness is that we want the system to have a majority of good IDs always in the system. When I say good ID, what I mean is that these IDs always follow the algorithm to the T. And the second thing that we want to ensure is that efficiency, that is, the computational cost is as low as possible, which is the main motivation for this work. So next we go into what our model is that we're working in currently. So the computational model is that we make the random oracle assumption, and we measure the computational cost in terms of the number of hash function evaluations. The next thing is the communication model, in which we assume that there's this diffuse protocol, a diffuse primitive. What this enables us is that it allows us to send messages to everybody, that is broadcast messages. Next, we say that we never learn who the sender of the message was. And finally, that the communication time is negligible when you compare it with computational time it requires to solve a puzzle. Finally, we assume the following adversarial model, that the computational power with the adversary is strictly less than a third. Second, the adversary knows what our algorithm is, but it does not have access to the random bits that we generate. And finally, we assume that this adversary is cryptographically bound. So then I come to the approach that we took to solve this problem. Is first I go into the naive approach, that is, initially there is a system which has a majority of good IDs, which is less than more than 2/3 of the total system in the network. And so now IDs are coming in, which are these IDs that come in. And these IDs, what we propose, instead of solving these puzzles continuously, that is what is happening in Bitcoin, we say that we only solve puzzles when the fraction of new IDs in the system has become greater than a third. In that case, we assign a puzzle to each one in the system, and we wait for one round to obtain solutions from these puzzles in the system. And what happens is that because Sybil IDs can only solve certain number of computational puzzles, which is proportional to the computational power it has, thus it can only provide solution to only one Sybil ID in this case, because we assume that the computational power is less than a third. And so only one of the new joining IDs remains in the system, and we are able to maintain the majority property for the system. So with this in mind, with this approach, there are a couple of attacks that are possible on our system. These attacks were the pre-computation attack. Second was that the cost was not commensurate. That is, the adversary could force the good IDs to pay a lot, even if it wasn't paying anything. And finally, how do you handle join and leave events efficiently? So in this case, for pre-computation, we assumed initially that there's a server, but we'll remove this assumption later, and the server actually broadcasts a random seed at the time when it sees that there has been a 1/3 change in the membership of the system, and every ID in the system, while solving the computational puzzle, has to include R as its input to the hash functions trying to solve. So this establishes that the solutions that are provided are always fresh. That is, you haven't pre-computed the solutions, and so you can limit the Sybil IDs. The second was that the cost was not commensurate. So for that case, that is that there was this attack that the adversary just kept on adding IDs to the network without paying any cost. So what this led to was that the good IDs kept on churning these puzzle solutions whenever it saw 1/3 change in the membership. And this led to a computational cost which was much, much higher than the adversary, that was 0 for the adversary. So in this case, what the solution was that for each ID that enters the system, we added an entrance cost for joining the system. So this led to what we call the entrance puzzle, and when the system as a whole was solving the puzzles, we called it the purge puzzle, because we were purging out the Sybil IDs in that case. And finally, the last problem was, suppose there were IDs that were continuously joining and leaving without actually changing the membership by much. In that case, we propose that instead of just counting, we take the symmetric difference in the membership of the IDs in the system. So what the symmetric difference does is that if there were IDs that just joined and left within the current frame of time, those IDs were not counted towards the change in the membership of the system. And so this is how we handled it. And in order to remove this assumption of the server, which I initially did, we replaced it with a quorum or a committee, which was elected from within the members of the system. I will not go into the details of the election, but due to time constraints. So finally, we have this result with this algorithm that we were able to guarantee the majority of good IDs is always there in the system. And suppose G is the total number of good IDs that enter the system throughout the lifetime of the system, and T is the computational cost to the adversary, then with high probability, the cost to the algorithm is big O of G plus T. That is, in case there is no attack, our cost is big O of G, whereas in case of an attack, the computational cost to the good IDs was big O of G plus T. So we were commensurate with computational cost to the adversary. So we were still not happy. We wanted to do something more intelligent. In that case, to reduce the cost further, what we did was the only place we found to be able to reduce the cost was to tune the difficulty of the entrance puzzles. So how we tuned this entrance difficulty was based on so suppose the good IDs, how do we define good IDs? It's based on how they behave in the system. So the entrance puzzles were basically then tuned with the difficulty such that it was the join rate of the current epoch, this current framework, this is an epoch in which we see less than a third of join events. So that divided by the average rate in the previous epoch. And so that was the next improvement we had. And I will just stuff right. So with this in mind, our efficiency actually became big O of J plus square root of J into T, where J is the average join rate and T is the average computation cost. Thank you.
Hello everyone, I am Archit Somani doing the PhD from IIT Hyderabad, India. So my today's presentation topic is an efficient framework for optimistic concurrent executions of a smart contract. Recently this work is accepted in the PDP conference, which is going to held in the Italy. So in my today's presentation topics, I'll explain like why we are executing the smart contract transactions and what is the need of executing them in the blockchain. Sorry for the delay. Yeah. I don't know why it's not working. Can you please check it? Sorry for the delay. Counter is still working? Oh, thank you. Thank you. I moved that in the yeah. So this is the plan for the presentations. First, I'll talk about introductions to blockchain, and then what is the bottleneck in the existing blockchain. Specifically, I'll talk about the Ethereum, and then what are the challenges we have faced to develop the smart contract transitions to be work concurrently, and then we propose the miner and validator concurrently. Then finally experimental evaluations, we have taken the benchmark from the Solidity documentations, and finally I'll conclude my slides. So let's talk about the blockchain. We already know till now, like, what is the blockchain? Blockchain is a decentralized distributed database or a ledger of records. It ensures that the records are tamper-proof but publicly readable. So this is the simple working of the blockchain, like how the blockchain will work. Let's suppose if A wants to transfer some money to B, then the transactions is broadcast to every other nodes in the miner, in the network, and then miner have to execute those transactions and form a block. And then that miner have to propose that block, which will go into the existing nodes, which we are calling as a validator. Validator have to validate those transactions, and then if the validation will be successful, then that particular block will be added or appended into the blockchain. And then that particular respective miner will get the award, and in the form of bitcoins. And finally, the money moves from A account to B account. So this is the simple functionality of blockchain, like how blockchain will work internally. Now I'm talking about the bottlenecks in existing blockchain, specifically to Ethereum. In the current era of multi-core processor, serial executions of the transactions by the miners and validator fail to utilize the core properly. Results have a poor throughput. So it will be more clear with this figure. Like here, if you will see in the left-hand side, serial executions of transactions. Here T1 and T2, I am considering two transactions which are going to work on the data items X and Y, which is exist in the shared memory. And write W stands for the write operations, and C1, C2 is the commit of the transactions T1 and T2. Here, if you will see, transactions T1 is working on the X data items and T2 is working on the Y data item. Both the operations are working on the different key or different data items. They don't have any conflict, but still they are in the existing scenario, they are executing in the serial way. First T1 will commit, and then after that T2 will start. So if you will apply the concurrency over there, then we can achieve the greater throughputs. How we can apply here, if you will see, when we can say two operations are in conflict. If two operations are working on the different data items, and at least one of the operations, if two operations are working on the same data items, and at least one of the operations should be the right, then we can say they are having a conflict. Here, if you will see, both the operations are working on the different keys, so they don't have any conflict, so we can execute them in any order. So here, after apply the multi-threading on both the transactions, we can execute them in any order, and there will be no conflict. So results will be same. So by adding the concurrency to the smart contract executions, we can achieve better efficiency and higher throughputs. So this is the motivations. Like in the current setting of the Ethereum, if the transactions are having a conflict, then they should have to follow some order. If they are not having a conflict, then they can execute in any order. But in the existing scenario, they are following the order. First T1 execute before the T2. So what are the challenges we have faced to execute the smart contract transitions to be concurrently? So concurrent executions of smart contract transitions may access the conflicting shared data. Identifying the conflicts at runtime is not straightforward because the languages are the Turing complete. Concurrent executions of the smart contract transitions by validator may incorrectly reject the valid block proposed by the miner. This will be more clear with this example. Here, if you will see the left-hand side, we are executing the two transitions T1 and T2 concurrently. Here, both the transitions operations are having a conflict because they are going to access the same shared data items. If, let's suppose, the miner execute them in concurrently, and it's the equivalent serial history is T1 followed by T2. And finally, the final state, which is got by the miner, which is having data items, and the value is 20. If the validator will not execute the transactions in the same order which is executed by the transactions, then the final state for the transactions T1 and T2 on data item X is 10. Eventually, the validator executed the transactions which is valid, but because validator is not following the same order which is proposed by the miner, that's why the final state is not matching. So how we can, these are the challenges we have faced to execute the smart contract transactions concurrently. So how we are resolving, I'll explain in the upcoming slides. So this is the proposed protocol, how we are executing the concurrent miner and validator. So we develop an efficient framework to execute the smart contract transitions concurrently by miner using optimistic software transition memory. First, I'll talk about what is the meaning of software transition memory. Software transition memory are a convenient programming interface to a programmer to access the shared memory using concurrent thread without worrying about the consistency issues. So user need not have to worry about any consistency issues like deadlock, live log, priority inversions. Everything will be handled by the STMs. So here the meaning of the optimistic is nothing but the effect of the transitions will come at the time of try commits. So this is the executions of concurrent miner. In the current setting, all the miners are competing to each other to propose a block. So I divided the phase in the task, like 1 to 6 are the phases. In TM stands for the transition memory. TM stands for the transition memory. First, it will take the set of transitions from the distributed shared memory, which is nothing but the clients. and then it will execute them in concurrent fashions. Here T1, T2 are going to execute concurrently. Here both the operations are working on different keys, so they can execute concurrently. Here we are using the optimistic software transition memory to execute them concurrently, and they will store the final state for both the data items X and Y. And we have to force the same order. Let's suppose if both the transitions are having a conflict, then the same order should have to be followed by the validator. Then only we will get the same final state. So how we are storing? We are storing the order in the form of graph. We are using the lock-free. We have built the lock-free concurrent graph library. It will capture the conflicting relations in the graph. Nodes are nothing but the transactions, and edges are the conflicting relations among them. And then finally at stage 4, it will compute the hash of the previous function or previous block. And at stage 5, it will form a block which consists of set of transactions, conflict graph, final state, and hash of the previous block. And finally, it will, after making the block, it will propose into the shared memory to the other nodes in the network, which is nothing but the validator. So this is the experimental evolutions. We have taken the benchmark from the Solidity documentations. We have taken simple auctions, coin, ballot, and we have proposed neuron, which is mixed the combinations of all the existing 3 benchmarks. So in the left-hand side, if you will see, we executed all the experiment on the 2 workload. The y-axis is nothing but the number of atom units, and x-axis is the speed up over the serial, and the right-hand side is nothing but the number of threads and speed up over the serial. So this is the conclusion. Like we introduced a novel way to execute the smart contract transitions by using the optimistic STMs. And we implemented the concurrent miner with the help of BTO and MBTO. But it's sorry, sir. Yeah. Thank you all. For more detail, you can refer the archive link. Yeah. Thank you.
Hello and welcome. My name is Jonas, and I'm currently working on the specification and verification of Hyperledger Fabric chain code. So, as Maurice and others have already stated lots of times in the past few days, smart contracts are, in a sense, pretty vulnerable because they manage value in some form, maybe digital currencies or access rights or something. They are usually visible to all concerned parties, and they usually cannot be changed, or it's annoying as hell to change them. So, in a way, more than with other programs, we need smart contracts to be correct upon deployment. There cannot be any software bugs, because software bugs can be exploited, and all the parties who want to exploit them are in our network, and they know how to exploit them. They can read them. So what we actually need for smart contracts is formal methods in order so that we can not only like test them and be partially sure that there are no bugs, but we need a mathematical formal proof of their correctness. Actually, this might be doable in the context of smart contracts, or at least more so than for other programs, because smart contracts are usually pretty compact. They are small. They don't have that many calls to external libraries or stuff that makes verification complicated in other contexts. Now, another thing that Maurice said is that the smart contracts are not contracts, and I agree with him on that, but I argue that smart contracts do actually need contracts. So if we talk about correctness of a smart contract, what do we actually need by that? We mean that the smart contract does what the programmer intended it to do when he wrote the program code, and it needs to, in a way, correctness is also what the caller of a smart contract expects that it does. And to establish consensus about what this correctness or what the intended behavior is, we need formal specification. We need a contract for the smart contract. Other stuff that we want to prove is termination or the absence of exceptional behavior. If we can prove all that, we can say that for our notion of correctness, the smart contract is correct, or one smart contract function is correct. We do this for Hyperledger Fabric, for the Hyperledger Fabric framework and for the chain code, which is their lingo for smart contract. Hyperledger Fabric is like an operating system for blockchain systems and for private and permissionless blockchain systems. I won't introduce it here in detail because it's rather complicated, but it has a lot to do with what we heard over the last 2 days, and I'm sure most of you would find it very interesting. One major point here is that smart contracts in Hyperledger Fabric can be written in Java, and we actually have a tool for that. It's called Key, and it's a tool for verification, full deductive functional verification of Java source code programs. To give you to give you a feeling about how this works, I'll show you an annotated program. So this might be a function in a smart contract. You can imagine like Solidity. In this case, of course, it's Java, but they're not too different in a way. And on that contract, we have a contract for the method in the Java modeling language, which specifies what we mean by correctness of this. For example, it states in the first line, normal behavior means it terminates without exception. And then it has a precondition and a postcondition. So if the two bids in this little toy auction that we have here, if the two bids are both greater than 0 and the asset that is given as a parameter is non-null, then the contract is meant to ensure the postcondition that comes afterwards. So if the first bid is greater than the second, the asset afterwards belongs to the first bidder. And the other way around. And if both bids are the same, then nothing changes on the ledger. This is a bit like pseudocode. It's slightly more complicated in an actual example probably, but just to give you a feeling about what kind of properties we want to specify here. So we know that after that function call, the following stuff can be guaranteed. Some of the challenges that we had to face is talking about serialization and object equivalence or equality after writing to the ledger and then afterwards reading it from the ledger. So if an object writes a node, if a node writes an object A to the ledger, he first serializes it, writes it, and then maybe later it's read and deserialized. So how can we prove in a formal way or infer in a proof tool that the two objects A and the object B that was read and deserialized are equal? So those were some of the challenges, or that was the biggest challenge to make that possible in our existing proof tool. Yeah, but we managed to do that, and in the end it worked quite nicely. So what we can do now, we have a specification of the Hyperledger Fabric API so that we can actually talk about smart contracts in the Java modeling language. We can specify these contracts. We can say what we mean when we say correct, they are correct or not. And verification is at the moment still a manual task, and it takes some time, and it's also, yeah, it's pretty complicated. It's not yet streamlined, but this is definitely a project for the next few months to streamline that and to make it, to make it possible for others to verify their own smart contracts. Another thing is working on distributed applications. That's something we did not do yet. We just work on a single function call, a single transaction of a smart contract, but we cannot yet prove invariance like no money is lost or no double spending occurs. That's not our category of verification at the moment, but we'd like to get there afterwards. And something that has also been mentioned is proof certificates. I think that is actually a very, very interesting idea in the context of smart contracts. So we prove that our function always does what we intended to do. Others can read the function, they can read the specification, and they can read our proof that it works, and so they can have high trust when calling the function that it doesn't eat all their money by some weird, subtle way that we introduce some error or something. Okay, thank you for your attention. If there are any questions, 10 seconds for the question. Okay, 10 seconds. is research in that area, not pertaining to smart contracts. There is research in that area, but it's, and from my guts, I'd say it's not yet really ready or really like working for industry grade programs. If there are any other questions, I'll be down at the port here.
Hello everyone, I'm Shweta from IIT Hyderabad, India. I'm here to present a topic titled An Innovative Approach to Achieve Compositionality Efficiently Using Multi-Version Object-Based Transactional System. So this is a joint project with the Michigan State University of Sandeep Kulkarni, and I have presented this work recently in SSS, and fortunately we get the Best Student Paper Award for this, and along with that the initial version of this work has got the Best Poster Award in NETIS 18 as well. So the outline of the presentation is, I'll start with the introduction to STM, then motivates towards the, why we motivated towards the MVO STM. Then I'll say something about the experimental results, like how much speed up we have gained through the, as compared to state-of-art STM, followed by conclusion and future work. So what is STM? STM stands for Software Transactional Memory System, which is a convenient programming interface for a programmer to access the shared memory using concurrent thread without worrying about the consistency issues. So just this is the working of STM, in which, like, just assume there is a memory which is nothing but shared memory, and we are having two transactions, transaction T1 and T2, and both are having their own local log. So it's an optimistic STM approach we are using, in which both any transaction, if anybody will write, then it will first write into its local log. And after doing the validation, so let's say the transaction T1 wants to read, it will always read from the shared memory. Similarly with the transaction T2 as well. And let's say transaction T1 wants to write, so it will write onto the local log. Then after doing all the write, before committing the transaction, it's an optimistic approach, that's why it will validate the transaction. Validating as in all the changes made by a particular transaction is consistent enough. Then the changes made by the particular transaction is going to be visible to the shared memory, and particular transaction will return abort, or return commit, sorry. So we can see like transaction T1 logs it permanent into the shared memory, and T1 is returning commit. Similarly, if any log is not consistent enough, then the particular transaction has to return abort. So here T2 is returning abort. So this was nothing but read-write level STM. So what is, we are working on the OSTM level, which is nothing but object-based STM, in which this is nothing but working on the higher level. This is, you can see like this one is the lower level STM or layer 0 STM, and we are working on this higher level. So what we have observed from the literature was sometimes working on higher level giving the better efficiency or concurrency than the lower level one. So this motivates us to work on the higher level. So after reaching to the OSTM, till that work has been done in the literature. So what we have motivated, can we get the more concurrency? The answer is yes. So how can we get the more concurrency? The best part is, from the literature we get motivated again, while maintaining the multiple version corresponding to each data item, we can improve the better concurrency, so that it will lead toward the better throughput as well. So here we can say there are two transactions T1 and T2. LU stands for lookup, and HT is nothing but hash table, and keys are K1 and K2. So what is happening over here? The transaction T1 is doing lookup on key K1 and K2 respectively. So what is happening? Here we are maintaining only single version. First I am explaining the disadvantage, then how we are overcoming the disadvantage using the multiple version. So here we can say like the transaction T1 is lookuping the key K2 is the older value, whereas this is transaction T1 is lookuping key K1 the newer value. That's why transaction T1 has to return abort. So instead of storing the single version, if we are maintaining the multiple version, so if the transaction T1 corresponding to key K1 will read the older value as well. In that sense, we can commit both the transaction, and the equivalent serial schedule will be T1 followed by T2. In that manner, we are reducing the the number of aborts, and this motivates us to implement the MVOSTM, that is multi-version object-based STMs. So the proposed STM, we have used the data structure as the lazy RB list, which is nothing but lazy red-black list. Here we are having the M buckets 1 to M, and the 2 sentinel nodes minus infinite and plus infinite is there. In between we are having the multiple keys. Red link is representing the deleted keys, whereas the blue link is representing the inserted key. That key is actually present in the list. So why we are motivating to do this? If let's say we wanted to search for the traverse for the key K7, and we are having only single list, then what will happen? We have to go through with the key K1, K3, K6 as well. So in that sense, while dividing into 2 parts, red and black, we are reducing the traversal time. So we propose this lazy RB list. And for the experiments, we have done this much for the lookup intensive workload and update intensive workload. So the figure A represents the lookup intensive workload with lookup 90%, insert 8%, and delete 2%. And as we can see, like MVOSTM is outperforming with the state of arts STM. So why is the reason behind it? Like it's performing almost 2.3 to almost 11% than existing state of arts. So, and whereas you can see like in the figure B, it's showing number of threads per second, number of time taken per thread. So what is happening over here for the update intensive workload, it's not showing that much performance. So the reason behind it, we can conclude like MVOSTM is favoring the read intensive workload. So for any application, we have to first identify which STM is working fast. So MVOSTM is nothing but it's favoring the read intensive workloads. So to conclude, and the future work is, we have combined the idea of multi-version and with the OSTM and proposed the MVOSTM, and which is harnessing the greater concurrency. And the HT-MVOSTM is giving this much of speed up than the existing state of arts. And for the future work, we can say like we can go through with the MVOSTM with starvation freedom, in which we have also started working on it. And next to it, like till now we have done with the list and hash table. So we can extend it to the hash table. We can extend for the stack, queue, tree, etc. as well. And apart from that, an interesting approach can also be the nesting in MVOSTM. And the last one is MVOSTM can also be helpful for the blockchain as well. For the concurrency purpose, we can use MVOSTM as well. So thank you so much for listening. This is the archive link. If you want to refer, then you can refer it. So any more questions? I think we're having that. Thank you.
Thank you. So, good afternoon, everyone. I'm here, Leila, from the Royal Institute of Technology in Stockholm, Sweden, where I'm doing a postdoc, together with Sharunas Gergisauskas. There is an S here, missed. I'm sorry for that. And actually, before starting into the topic, I will just give a bit of a history of how we kind of fall into working into things related to blockchains. So myself, I come from a privacy access control background. This is what I did my PhD on. And then I joined this group at KTH, who are distributed systems and distributed computing people doing all things especially with graphs and graph theory. So we tried to find something in between. And at the beginning, we started from trying to solve this problem of these auditable privacy agreements in web service consumption. It's this classical thing in which you open a website or you want to consume a web service, and then it tells you, do you agree to all the terms of service? We all of us just click and go ahead, and we don't know what we agreed to. And so the initial idea was to try to automate this with some tool that will just whenever you click, I agree, it parses the agreement, gets all the most important things, and just puts them in some type of database, which guarantees both transparency, auditability, and also that is not centralized. We don't want to trust anyone on this like kind of game. And so we wanted something peer-to-peer. And this is where we asked the question, can blockchain come in to help, like in the picture? And the answer was yes, we can use it as like an infrastructure and use it as a black box, maybe just like to put in our transactions or our contracts. But then we got into these things. First, transactions on blockchains as they exist today, they cost. So anyone who wants to use the service will have to pay some fee or something in terms of some cryptocurrency. The second thing is that we are people who care about the environment, and blockchains as they are today, they have like huge CO2 emissions, and we don't want that. And the third thing is that we really want something that is decentralized. And then the fact is, blockchains are moving more towards centralization with all these mining pools and things with what's existing nowadays. And so it's not even that now we have to trust one single server that is known. We are obliged to trust virtually some individuals that we don't even know. And so we didn't want that. So then we fell into like trying to find some alternatives. Okay, what can we do? We found that there is this kind of permission versus permissionless, so maybe we could use the permissioned model. But again, this permissioned model will just throw us again into centralization, because you need some entity that will give you this credential or this identity confirmation to join the system. We don't want this either. So we went into exploring what's out there. We found that there is proof of work with all these things, like first with the energy consumption. Then we found that there is something called proof of stake. But then which like does much better in terms of CO2 emission, but both of them, they rely on cryptocurrencies, and so we are kind of linked to a financial type kind of a blockchain. Also, both of them, they have like this issue of like centralization. So we asked the question, can we find something that will fill up here, this space, with some proof of something else? Well, since we are also working with trusts, with graphs and stuff like that, we asked what we need. We need to solve consensus, which is basically, as we've seen yesterday and today also, vote for a leader, which is leader election, which is partially two parts, like Itai said yesterday, who is allowed to vote and how do we vote. And then why do we need that much harsh mining and that much CO2 emission? It's basically because we don't know anyone and we don't trust anyone. So then we asked the question, can we actually just use proof of work as it is, because it provides nice guarantees and it provides nice solutions, but just waive the difficulty, because it's the one that gives us all these CO2 emissions, by some trust, using trust networks. Yeah, so the idea was getting into exploring this point of waiving proof of work by trust. Trust is inherent to many use cases, and I had so many people yesterday asking over the poster, what are the use cases that you thought about? And then we can, of course, talk about that again over the poster. But this could be like web service users, like what we said now. It could be like users of these web services. It could be like, let's say, for example, flight reservation companies, or all these people in this travel arrangement agencies, etc. Peers can develop trust among each other through time from all the transactions that we perform among each other. And so the more you prove through time that you are honest, I will just like tend to increase your reputation to trust you more. And so each peer will gain a trust value in this trust network over the time, or in the, let's say, blockchain system between quotes here. And the more trusted peers in our model will just be privileged to mine at a much lower difficulty. So basically, it's just this idea of like selecting a committee, like Itai said yesterday. So we select a committee out of all like the existing kind of people in the community to perform proof of work with a low difficulty. So we came with this proof of work, proof of trust framework. So we assume that we have a trust graph emergence model that we designed later on, and this one is like, could be extracted from the domain or knowledge application, could be linked from social networks, or could be also be freely expressed by the members, and this is what we adopt in our solution. So you freely and subjectively say, I do trust Maurice, and I do trust, I don't know, X and Y, and the others that I don't trust, I just don't announce any transaction towards them. Then this will just make us constitute something called a trust graph, and because we need also to agree on the status of this trust graph, we just suggest of putting it into the consensus blockchain itself. So this becomes solved, and then based on this trust graph, we run whatever kind of centrality measure on the graph, and we extract some trust measure for every node, or centrality measure basically, and based on it, we do this kind of waived selection for proof of work. So the basic idea is this, is that we select just some trusted candidate set. So it's a little kind of smaller committee, and it's the committee that runs the consensus algorithm using some low difficulty proof of work. But then this will just like have some problems, and most of them are related to this skewed distribution of everything like we have in nature. So the highest, this is just like the frequency, the number of people, and the trust that they have. And then we see that the majority of people, they will have lower trust, and then it's just a few minority, a few elites that will be like in this top trusted set. And then we will also fall into centralization, which is one of the things that we didn't want at the beginning. So yeah, a few highly trusted peers may end up monopolizing the network, and we don't want that. There is another thing, is the, I think I didn't put it in the slides, and it's with regard to Sybils. So of course there could be also this spam farming, since we are living this like open in the network, and we are working under a permissionless model in which we don't manage identities. There is nothing that prevents someone from just creating multiple accounts and then boosting their trust in the network. So for this, we are just using some little tricks. The first one is no flat waiving, which means that we don't just like make this committee selection. Instead of that, we make many committees that are ordered based on their trust. And then okay. So I'll skip all of these things, and I will come here. Yeah. So we think that we could fill the space to some extent. If you want for any further discussion, there is the poster downstairs, and I will be there both today and tomorrow. I think I signed up for today and tomorrow. Thank you.
Okay, so my name is Oded Naor. This is joint work, which is still work in progress with Phil Dayani and Myers, Ari Jules, and Itai Eyal. And I was supposed to talk about a different issue today, but because voting came up yesterday, I decided to talk about ongoing work that we're doing. So let's start with dividing the two possibilities of voting on-chain. So let's start with democratic elections. So electronic elections is a well-studied issue. It's been on many venues. The term coercion freeness, which was coined by Ari Jules in 2005, means various attack models and how to ensure that voting schemes are secure against them. And usually all of these voting schemes require some kind of trusted parties, for example, for tallying the votes. It also usually requires some type of a bulletin board to post, let's say, the votes, the proof that the votes were tallied correctly, etc., etc. And it appears like blockchain may actually be some magic pills for these issues. You can use smart contracts to tally the votes. You can use the blockchain itself as a bulletin board. But what I want to say is that blockchain isn't a solution for everything. So it's a real problem. In the midterm elections a month ago, West Virginia deployed absentee votes using blockchain, Hyperledger Fabric for that, say. And I will quote Ron Rivest, a known cryptographer, who says that best practices for voting is like best practices for drunk driving, meaning just don't do it. But I will talk a little bit about protocol governance. So you can actually use the blockchain itself to hold a vote for protocol changes. Gun talked about it an hour ago. You can vote on certain parameters of the protocol itself. Consensus, in a way, is a form of a vote. And actually, in the past, naive implementations of voting schemes on-chain for protocol governance has been deployed. So the DAO attack, which was in a few years ago, actually deployed what was called a carbon vote to decide should we fork the Ethereum blockchain or not. And it was a very naive implementation. I won't go into the details, but with a very simple smart contract, you can bribe and buy votes very easily. That was because you can just observe the blockchain and the votes weren't anonymous. There was no privacy on the vote itself. I will also say that trusted hardware, how many of you know what TEEs are or SGX is? So an SGX, okay, that's good. An SGX is a form of hardware that ensures confidentiality and integrity. The current only vendor that ships or creates these types of TEEs is Intel. But as we advance in time, more and more vendors potentially will create such hardware. But this hardware can actually be used to attack voting schemes and be used maliciously. So if we have Alice, who runs a TEE, and we have Bob, which is malicious and wants to buy Alice's vote on chain, Alice can run and say, I will only vote for a certain candidate. And Bob will say, I will only pay you once you vote for that way. And by using those TEEs, we can gain trust between these trustful parties, someone who wants to buy a vote and someone who wants to sell it. There is also the notion of dark DAO, which I won't go into, but the TEEs, we can use them to create the DAO for malicious attacks. Everything is off-chain. We just use the SGX, the TEEs, for getting trust between the parties. And I will summarize by saying that blockchain is not a magic pill. Elections, at least now, are way too important for us to use. We don't understand fully the technology. We shouldn't use blockchains or any sort of electronic voting before we truly understand and put our democracy in the hands of electronic voting. Other votes need to be run after really careful thoughts. Old naive implementations are really easily prone to vote buying attacks, coercion attacks. I will say that there are 2 blog posts in the morning describing all these issues, and you're welcome to look at them, and in the following month we'll publish a paper demonstrating these kinds of attack and extending more on the issue of using trusted hardware to attack certain voting schemes and other cool stuff. So I don't know how much time I have, but if you have any questions, you may ask. Yes. So like I said, the security guarantees that we want from an electronic voting scheme was coined as coercion freeness in 2005, and there are certain schemes which aren't practical actually, but can be used to realize those guarantees. We will try to do a constructive approach, but again, it's using blockchain as a magic pill is not a solution. There are ways to get these guarantees we want, but it's not that easy. I'm saying that implementing a naive voting scheme is very prone to attacks. Yes. Zero knowledge is part of all these schemes. For example, Jeremy Clark has a proposed solution that uses zero knowledge. And yes, it's part of the proof. But again, you need to, zero knowledge is just like blockchains. It's not a magic pill. It needs to be used precisely, and it needs to have rigorous proofs that it achieves the desired security guarantees that we actually want. Oh, yeah. Because when you look at CoinMarketCap and you see that Bitcoin is worth $20,000, you get a hype. But just because the stuff I said, it can be used as smart contracts, can be used to automate part of the voting scheme, and it can be used as a bulletin board. So the words match, but it's not like you can use it again. It's not like a flash drive you stick and it works. It needs to be adapted, and it's way too important. Democracy is way too important for us to entrust it on blockchain. There's an XKCD tour about any subject. So, thank you.
all of you. I'm Subodh. I'm a faculty member in the Department of Computer Science at IIT Delhi, and this work appeared earlier this year in NDSS, and it's a joint work with Sukrit, Seep, and Mohan from IBM Research India. And it primarily deals with looking at smart contracts and trying to establish provenance that smart contracts are indeed doing what they are supposed to do. I don't need to sort of motivate you why we need to look at smart contracts. Morris spoke about it yesterday, Itai spoke about it today morning, and Jonas just a while back gave you a very nice motivation why smart contracts need to be verified and validated against a correctness specification. I would quickly just zip past these slides and go to the fact that there are tons of vulnerabilities that exist in smart contracts, and a class of vulnerability was discussed yesterday by Morris, which is reentrancy attacks, which means if somebody is invoking a transaction, a smart contract is being executed, and a call within a smart contract ends up re-invoking the same code, then potentially you can have bad things happening. In addition to that, there are a lot of other things that are fishy in the way these smart contracts are developed. For example, there is no good way to handle exceptions. If you are invoking a smart contract, so within your smart contract, if you are explicitly sending messages via a send call and an exception happens, then it's going to be treated very differently as opposed to those calls were made by an explicit call statement. Right? So exception semantics differ from one construct to other construct. I'm not going to essentially go in detail about these things, except the fact that exceptions are not uniquely. There's no uniform way of handling exceptions. Reentrancy is a huge problem. Typecasts are a problem. Another huge class of vulnerabilities that exist in smart contracts is integer underflows and overflows, which means that if you're executing smart contracts where business logic is dealing with actual money and you have integer underflows and overflows, then it's a real cause of concern. So what did we do? So the takeaway from this slide is the fact that there's a very nice survey of attacks that could be orchestrated on smart contracts on Ethereum. And this is the paper, so you can go and have a look at it. What did we do? So essentially, we mined the existing sources where smart contracts are put up, source code of smart contracts are put up, Etherscan being one of them. And so we had the source code with us. And then we created a property, or rather a semantic preserving translator from Solidity, or Go for that matter, to LLVM bitcode. So the first component of our work was essentially a semantic preserving program translator. So given a smart contract program, P, we translated it into P prime, where P prime preserved all the behaviors of P, but generated code was LLVM bitcode. And LLVM, yes? That's a very good question. So LLVM is designed for languages such as C, right? So sequential program are compiled into LLVM bitcode, so bytecode. So we had to deal with few things. So I would welcome you to look at the paper. There were a lot of things that we had to do to make sure that LLVM bitcode mimics the semantics of EVM. I don't have the time to discuss, but we can take this discussion offline. The next thing was, given these set of vulnerabilities, how do we, so we don't have a good way of identifying property violations. So the kind of properties that we are interested in is that the smart contract is safe with respect to certain correctness specification, which is essentially our business logic. Jonas spoke about it, right? Nobody is giving you that specification to begin with. So what we so we assume that the developer has some knowledge of where the property violations can happen and smartly inserts assert expressions. If the developer doesn't do that, then it provides a high-level specification to us in a domain-specific language, and through that we could figure out the right control locations where we could insert assert expressions, assert statements. This was done in the LLVM bitcode, and once we had the transform program P prime with the right assert statements introduced into the LLVM bitcode, then we fed this transform program P prime to an off-the-shelf symbolic model checker. So essentially, we relied on bounded model checking because most smart contract executions are, so smart contract languages are essentially Turing complete, but their behaviors are quasi-Turing complete because, so Itai spoke about that fact that the behaviors are all terminating because of the fact that you can supply only so much gas to smart contracts execution. So bounded model checking sort of fits well here. And we use CHON. This is a tool, symbolic model checker, developed by Ari Garfinkel, which essentially generates verification conditions in the form of constrained HON clauses, and they have their own decision procedure at the back of it. So we discharged all these verification conditions in a matter of minutes, and the big takeaway was that in a matter of 5 minutes, we could identify vulnerabilities in almost 22,000 smart contracts that are publicly available for Ethereum, amounting to almost $300 million worth of vulnerability or loss. So that was the big takeaway of our paper. I just want to end this talk with what's the next thing that we want to look at. I mean, it clearly got us interested in smart contracts, but to our surprise, we realized that verification as a process is not a first-class feature in the entire consensus process, which means that if a smart contract developer is deviant, they could introduce vulnerabilities in the smart contract, put it up with a known set of input-output pairs, right? So the miners can essentially look at that, and they have no way to establish whether the smart contracts are indeed acting according to their correctness specification. So we want to do something what Jonas was speaking earlier. Could we use some proof certificates and introduce verification as a first-class feature of blockchains? With that, I'll end. Thanks. I'm open for